Welcome to G Fun Facts Online. The ground beneath our feet feels solid, permanent. But what if I told you that over geological time, huge chunks of our planet's crust, sections larger than continents, have simply vanished? This isn't science fiction. It's one of the biggest puzzles in geology. The case of the missing crust. Scientists are on a hunt for this lost lithosphere, a journey that takes us from the bottom of the Grand Canyon to the scorching depths of the Earth's mantle, revealing that our planet is a giant, restless recycling machine. Let's dig in. Our planet's rigid outer shell is called the lithosphere. It's not one solid piece, but is broken into about a dozen major tectonic plates. These plates are constantly moving, driven by heat from the Earth's core. The theory of plate tectonics explains how this movement causes earthquakes, volcanoes, and builds mountains. A key part of this theory is recycling. At mid-ocean ridges, new crust is born as magma rises up. To keep the Earth from expanding, old crust must be destroyed elsewhere. This happens at subduction zones, where denser oceanic crust dives beneath another plate and sinks back into the mantle. The recycling of oceanic crust is well understood. But what about the continents? Continental crust is thick and buoyant, like a cork in water. For a long time, geologists thought it was too light to sink, and was therefore permanent. But a growing pile of evidence shows that this isn't true. Huge volumes of continental crust have also been lost, swallowed back into the deep earth. This is the heart of the mystery. One of the most stunning pieces of evidence is a feature called the Great Unconformity. First identified in the Grand Canyon, it's a stark line in the rock layers. Below the line, you have billion-year-old rock. Immediately above it, you find rock that's only about 500 million years old. That's a gap of over 500 million years of geological history, just gone. It's like finding a book where chapters 3 through 7 have been completely ripped out. And this isn't just a local feature. The Great Unconformity is found on every single continent. What could possibly cause such a massive, planet-wide erasure of rock? The leading theory is as dramatic as it sounds: snowball Earth. The hypothesis suggests that between 720 and 635 million years ago, our entire planet froze over, from poles to equator. Imagine glaciers, kilometers thick, covering the continents. The immense weight and grinding power of this ice would have been a planetary-scale sandblaster, scraping away an estimated average of 3 to 5 kilometers of rock from the continent's surface. This pulverized rock was then dumped into the oceans. The theory neatly explains the sheer scale of the missing rock layers. It also explains a curious lack of asteroid impact craters, older than this period. The glacial scouring would have erased them. While snowball Earth is the front-runner, some scientists suggest the erosion might have been linked to the breakup of supercontinents, which causes major changes in sea level. But whatever the cause, the Great Unconformity is a silent testament to the Earth's power to rewrite its own history. Surface erosion is only part of the story. Deeper inside the planet, there are even more powerful mechanisms that swallow the crust. The main one is subduction. As we mentioned, this is where one plate slides under another. While it primarily recycles oceanic crust, we now know that continental crust can get caught in the process. When two continents collide, or when a continent is dragged towards a subduction zone, its leading edge can be pulled down deep into the mantle. This was a revolutionary idea, challenging the notion that continents are unsinkable. Then there's a more mysterious process called delamination. Imagine a mountain range like the Andes or the Himalayas. As the crust thickens to form the mountains, its dense lower part, the lithospheric root, can become heavy and unstable. Delamination is when this dense root detaches or peels away and sinks into the hotter mantle below. The loss of this heavy anchor causes the surface above to rebound and rise. It also allows hot mantle material to well up, often triggering widespread volcanism. A third mechanism is tectonic erosion. This is a slower, steadier process. At a subduction zone, the downgoing plate doesn't just slide smoothly. It grinds against the bottom of the overriding plate, scraping material off like a giant file. Over millions of years, this steady abrasion can remove enormous amounts of continental crust. So how do we know any of this is actually happening? We can't just drill down hundreds of kilometers. Instead, geologists have become detectives, using incredible tools to find the fingerprints of this lost crust. The most powerful tool is seismic tomography. It works like a medical CT scan for the entire planet. Earthquakes send seismic waves traveling through the Earth. By measuring how long these waves take to reach thousands of sensors around the globe, scientists can build a 3D map of the mantle. Cold, dense material, like a sunken tectonic plate, allows seismic waves to travel faster. Hotter material slows them down. Using this technique, scientists can literally see the ghostly outlines of subducted slabs sinking deep into the mantle, sometimes thousands of kilometers down. They've seen these cold anomalies under the Pacific Ring of Fire, the Mediterranean, and the Himalayas, providing direct evidence of crustal recycling. We also find clues in the chemistry of volcanoes. When recycled crust melts in the mantle, it can become part of new magma that erupts on the surface. This recycled material has a unique chemical signature, different from the surrounding mantle. By analyzing the isotopes of elements like strontium and lead in volcanic rocks, scientists can identify magma that contains melted, ancient continental crust. It's a chemical fingerprint proving that what goes down can, in a way, come back up. We even get physical messages from the mantle. Sometimes, volcanic eruptions bring up chunks of rock from deep within the Earth, called xenoliths. Occasionally, these are identifiable fragments of subducted crust. Even diamonds can carry the story. Formed under immense pressure, diamonds sometimes contain tiny mineral inclusions with a chemical composition that could only have come from surface rocks, meaning the very carbon of the diamond was once part of the Earth's skin. Let's take a quick tour of some global hotspots for missing crust. First, the Himalayas and the Tibetan Plateau, formed by the colossal collision of India and Eurasia. For a long time, we thought the crust was just thickening. But seismic tomography shows that a huge slab of the Indian continental plate has actually been subducted deep beneath Tibet. On top of that, there's evidence that the base of the now overly thick Tibetan plateau is delaminating, sinking into the mantle, which helps explain the plateau's continued uplift and volcanism. Next, the Andes Mountains in South America. They are a classic result of the Nazca oceanic plate subducting under the South American continent. But it's also a site of massive crustal loss. Tectonic erosion has scraped away vast amounts of the continent's edge from below. And in the central Andes, delamination of the lithospheric root is thought to be responsible for the dramatic uplift of the high Altiplano Plateau. Closer to home for North Americans, there's the Sierra Nevada in California. Its majestic granite peaks are the remnants of an ancient volcanic chain. But why are they so high today, far from an active plate boundary? The answer appears to be delamination. The dense root that once supported the ancient volcanoes detached and sank, causing the overlying mountain range to pop up like a cork, a process that also triggered a new wave of volcanism in the area. The Mediterranean is another hotspot, a complex jigsaw puzzle of colliding plates. Seismic imaging reveals a graveyard of subducted slabs beneath the sea, remnants of ancient oceans that have been completely swallowed. So why does all this matter? The recycling of our planet's crust is a fundamental process that shapes our world. It's a key driver in the creation of continents and the supercontinent cycle, where landmasses periodically assemble and break apart. It's also Earth's primary chemical engine. When crust subducts, it carries water and carbon into the mantle, changing its composition and influencing volcanism. This recycling process is also responsible for concentrating many of our most valuable mineral resources, like copper and gold, which often form in the volcanic systems created by subduction. And, of course, these very processes create some of our planet's greatest hazards: the massive earthquakes and tsunamis at subduction zones, and the explosive volcanoes that sit above them. The study of the Earth's missing crust is a frontier of science. Big questions remain: how much continental crust has truly been lost over Earth's history? And when did this modern style of plate tectonics even begin? As new technologies allow us to peer deeper and model the Earth's interior with greater accuracy, we get closer to answering these questions. The story of the missing crust shows us that we live on a world that is constantly destroying and renewing itself. The ground beneath us is not a permanent fixture, but the ever-changing skin of a dynamic, living planet. The puzzle is far from solved, but each new clue brings us closer to understanding the restless heart of our world.